Welcome back. We're on part 2 of hypothesis testing, and also the next to the last one. The last time we were talking about hypothesis testing in general. This time we're talking about actually doing a hypothesis test. And to make things as simple as possible to begin, we're talking about population means. That means averages. Next time we'll talk about population proportions. Sort of like what percentage of the people are going to vote for you in the next election. But for now, hypothesis testing for population means is where we're going to go. And we'll get the pen ready here. There's one ready to go. And okay, we've got everything ready to go. It's far away. Alright, so we're going to talk about 1 and 2 tailed hypothesis tests. Remember, you start with the claims. We're talking about population means, and we'll make some reference to type 1 and type 2 errors in hypothesis tests. So first of all, 1-tailed, because they're a tiny bit easier anyway. So let's look at this situation where you have Columbia College, and they're saying that the mean average starting salary of their graduates is $39,000. Not too bad, I guess. And there's an organization that thinks that it might be exaggerated. So, of course, what do? They conduct a hypothesis test. Let's check and see what the evidence says about this. Now, remember once more, we're not going to prove anything, but we can say that the evidence sort of leans us in one direction or the other. Let's see what happens about that $39,000 mean starting salary. First of all, notice that the mean starting salary was said to be $39,000, so that becomes our null hypothesis. Because, why? Because there's an equal in that statement. Now, that is the standard. That's what we believe right now, or to begin with. And the claim is that that's exaggerated. In other words, it's too high. Let's see what happens. This is a story, remember? So enjoy the story and do some hypothesis testing at the same time. Since we've got a less than form, remember that means it's pointed in the left direction. We've got a left-tailed hypothesis test. That's important. So we've got a random sample of 100. Of course, that means n equals 100 for us. And the mean salary from the sample is $37,000. It does look as though there's some possibility that $39,000 could be suspect. Let's see what happens. We're going to follow the 4-step hypothesis test that we talked about earlier. Now this page 376 is on a different book. It's on the book Statistical Reasoning for Everyday Life, just in case you're interested. Start with step 1. We've identified the population parameter of interest, that's the mean, and the 39,000. We need the null and alternate hypotheses. We're going to get a sample, and we're going to measure that to find out what the sample size is and the sample mean. So we're going to be talking about a sampling distribution, since what we're going to get from the sample is a sample mean. Step 3, we're going to find out how likely it is, this is very important, the likelihood of finding that sample mean as extreme or greater. And that's assuming that the null hypothesis is true. So the question becomes this: We've got a sample of size 100. From our sample, our X bar is the $37,000. When or less, is that a possibility? How likely it is that we'll have actually a starting salary of $37,000 or less, more extreme, when the mean is actually $39,000. So this is one point in a distribution because there are lots of possible sample means. Remember, this is one of them. We're going to assume that the null hypothesis, that's this, is true. Here's a picture of it. Here's our 39,000. That's our established mean for the time being. And this is the value that we got for X bar that makes us a little bit suspicious about whether the 39,000 is really true. It is less than the 39,000, but is it extreme enough that we can reject the null hypothesis? So, first of all, and this works with a lot of things, that's why I'm leaving this in here. We don't have to use the standard score, but that's a good, excuse the expression, standard way of working with hypothesis tests. Using this, getting a z-score, you can use that z-score to find the p-value or critical value, either one. So finding the standard score is a good thing to do anyway. Since the sampling distribution, remember, we know that's going to be normal because n is over 30. And the z-score is going to tell us how many standard deviations that 37,000 is above or below the mean of the distribution. So here's the distribution of the sample means. Remember, for sample means, we don't use the standard deviation. We use the standard deviation divided by the square root of n. A slight adjustment because we're talking about a distribution of sample means. Here basically is how we find that z-score. We take the mean that we got, that's X bar, as you can see over here, minus the population mean, that's mu, over the standard deviation of the sampling distribution. This somewhat complicated looking thing, not a big deal though, because if you do this in advance, then it doesn't look that strange. So put all this together and we can find our z-score. The only thing is, we don't know the population standard deviation. That's a downer, right? But if we don't know it, what's the best bet? How about the sample standard deviation? In this case, it's 6150 for those 100 salaries that we used in the sample. So here then is our, should be this. Standard deviation of the sampling distribution is the standard deviation divided by the square root of n. So I need to fix slide 9. But anyway, here's our standard error, which is this. That's what we're going to use in place of the population standard deviation that we don't know. So here we go. Here's our z-score, negative 3.25. So we might say to ourselves, that's how many standard deviations our sample mean is away from what we think is the mean. That's pretty far. What does that tell us? Well, when we draw a random sample, there are a lot of samples we could have gotten. That's the one we got. It gives the sample mean and the population standard deviation and the claimed population mean. Using those, we get the standard score, which is down here, that's the z-score, for our x bar. Next, we're going to find the critical values. In other words, where are our cutoff points? Now, back here somewhere, because this is the mean that we expect to be true. If this is far enough away, then we're going to reject the null because this would be the null. This is what we think was the mean. If our z-score is back here far enough at a critical value, far enough away, we're going to say, I don't think I can justify calling the mean 39,000 anymore. So we're going to go with significance at the 0.05 level. It's sort of the standard. We can use different ones, but we have to do it before we get our sample. For a left-tailed test, we're looking over here. If our x bar falls inside this rejection region or critical region, we're going to reject the null hypothesis. Now we can look at Appendix A in that book, but we don't need to. We can use our inverse norm. Since it's a left-tailed test, we have an area of 0.05, and of course 0 and 1 because it's z. And this will give us our critical cutoff point. So we get negative 1.645. So what does that tell us? It means if the z-score we get from our test is less than the negative 1.645, we're going to reject the null hypothesis. So here's a picture of what we're doing. Here's where 39,000 is. That's representing the null hypothesis. Here's our cutoff, negative 1.645. We're looking to see whether our sample mean is back in this green area. If our z-score is less than or equal to that critical value, we're going to reject the null. Here we go. So for a left-tailed test, we're going to reject the null if z is less than or equal to negative 1.645. And that's because we're talking about the 0.05 level of significance. If it's greater than that, if it's greater than that, we'll fail to reject it. If we want the 1% level of significance, we would be looking at a stronger case. If our z-score is less than negative 2.33, then we'll reject. And these are the values we would use if it were a right-tailed test, if we thought that the 39,000 was too small. So, which one would you use? 0.01 is going to give us stronger evidence. Why is that so? Think about it. So if the null hypothesis is true, then we're saying the mean starting salary is $39,000. Per sample says $37,000. What does that say? Do we reject or not reject the null hypothesis? Well, we got the 37,000. That gave us a standard score, which I prefer to call ZT because it's for our test statistic, and it's negative 3.25 standard deviations to the left of that mean that we're accepting for the time being. The result is significant because that's what we got from our sample, is less than the critical value, being a left-tailed test. It's also significant at 0.01 level, because that standard score is negative 2.33, and our negative 3.25 is even less than that. So we have a strong reason to reject the null hypothesis. So we believe that the starting salary average was exaggerated. Next, that's using critical values. How about using p-values? That's the one that I said we would sort of emphasize, although you can do it both ways. Now here's the important part. For the p-value part or way of testing, the p-value is the probability of finding a sample mean as extreme or more extreme than the one found, if the null hypothesis is true, of course. How unusual and that's in terms of probability. P-value, capital P, by the way. For left-tailed test, like we've just done, sample mean less than or equal to at 37,000 is the area under the curve to the left of the sample mean. In other words, like that, which you can see right there. Here's the critical area. If our sample gave us a z value back here, we'll reject the null. If it's a right-tailed test, it would be a similar thing, except the mirror image. And this is where if we had our test value giving us a probability out here that's very small, we would reject the null for the right-tailed test. So here's your summary. You can pause it and read this, maybe even copy it. Decide whether to reject the null hypothesis. It's whether a sample as extreme as the one found in the hypothesis test is likely or unlikely. P-value small, not small. That's what you can use, sort of. It's not very scientific, but that gives you a gut feeling for how it goes. So we'll find the z-value for our score. Here's the score itself. This is the standardized version of that, and we can use that to find the p-value. Compare it. Well, you don't have to do this actually. You can use inverse norm to find out what those critical values are like. determine that p-value from the score tables or from your TI A4 or similar calculator. If it's statistically significant, and that's usually at one of these two significance levels, 0.05 or 0.01, then you reject the null hypothesis. If it's not in one of those regions, not small enough p-value, we do not reject the null. So here's a case just to get us thinking a little bit more concretely. So we've got a rental car fleet owner, and he thinks that the mean annual mileage of his cars is greater than the 12,000 miles that's considered to be nationally. So what does he do, of course? He gets a random sample. In his case, he samples 225 of his cars and gets the sample mean of their mileage. What he gets from his sample is X bar is 12,375. The next question becomes, is that extreme enough to reject the null hypothesis or not? We also found by doing that sample, we have a sample standard deviation of 3,415 miles. We're going to find the level of statistical significance and the p-value for that hypothesis test, and then interpret it. So first of all, here's our sample mean. We're going to find what that translates to as a z-value. Take that value, subtract it from the value we're comparing it with, the 12,000, divide by the standard deviation. Well, the only standard deviation we have is from the sample, so we'll use that to get our sample z-score. There's our z-score. And what I like to call this is z sub t, because we're using this value along with this to find out how extreme this is, or how many standard deviations away from the mean is our sample. 2.33 standard deviations. That's pretty far. Is it far enough? The critical value is 1.645. That's because we're talking about a 0.05 level of significance. You can get the p-value from our calculator. Normal CDF. Since it's a right-tailed test, we'd have 12,000, what was it? 12,375 to infinity, whichever way you want to write that. Normal CDF, put your mean and standard deviation here. In this case, you might have to use, we'll have to use that 12,000 here, and what was the standard deviation? 2415. So p-value using those is 0.0099, or in other words, just about 0.01. Now, how about a two-tailed test? The same thing applies, except that we've got a not equal to instead of equal to, or greater than or less than, sorry. Two-tailed tests, one thing we have to remember is that 0.05 is split between the left side and the right side. So when we get our p-value, we're going to have to double it to compare it against our level of significance. You can use Appendix A, of course, if you want to. I'm not suggesting that. 25th percentile will correspond to a standard score of negative 1.96, and the top percentile will correspond to positive 1.96. These are the critical values for this two-tailed test, or any two-tailed test at the 0.05 level. Here's what it looks like. Well, here's our 12,000, which is our null hypothesis. And we're going to reject the null hypothesis if we've got a very large value of a mean or a very small value. So we end up with our p-value. We're going to double that because it's a two-tailed test. So the significance at the 0.01 level, you might become familiar with this. The critical values for that for a two-tailed test are, is the z value less than negative 2.575, or is the z value greater than positive 2.575? Either of those is true, you reject the null. So use your value of x bar and get the p-value for your test, and then double it. Don't forget. So here's another example. A drug company. They want to make sure that its tablets really contain 500 milligrams. Now, we've been using 0.05 as our level of significance. This might be pretty important. If you take one of these aspirin tablets, you want to make sure you get some relief, right? And you don't want to overdose. So it really needs to be close to 500 milligrams. So there's our population mean. We want it to be equal, not over, not under. And there's our alternate hypothesis, not 500 milligrams. We get a sample, we take 100 tablets. Here's the average we get. Does this really suggest that it's too strong, or in the other case, too weak? We know that the population standard deviation is 7.0. That helps us with our calculations. Our standard score, remember this is a sample, so we use a standard error, which is the standard deviation of the sampling distribution. There's our test z value. You can see it's toward the right side. Is it far enough to the right side to reject the null? Actually, no. It's not over 2.575. So, since it isn't, oops. So reject to one level, not the other level. So the area to the left is standard score. For this example is 2.14. That gives us this p-value. For one-tailed test, it would be the area to the right, and would subtract from 1. That should sound familiar because we've got symmetry with our normal distribution. And because it's a two-tailed test, we multiply the p-value by 2, and that's the p-value we'll use in determination of whether we reject the null or not. So this is what we'll use. We'll compare it to our level of significance. See if it's smaller than that level. If it's smaller, we'll reject the null. 2 errors are possible. And we're going to use the legal analogy. You might connect with this one. The null hypothesis is the defendant is innocent. Innocent until proven guilty, right? One error is the defendant is guilty, is concluding as guilty, but they're innocent. Think of this. If you were innocent and you were declared guilty, that's one kind of error. The other kind of error is you're guilty, but you get off as being declared innocent. That's the other kind of error. That's the same kind of errors, same kinds of errors we're talking about here. Type 1 and type 2 errors. First, the null hypothesis is wrongly rejected is a type 1 error. Type 2 error, we wrongly failed to reject the null when we should have. Here's a table that gives you an idea of how these work. This is the reality up here. If it's true, reject the null, we made a mistake. If it's true, we do not reject the null, we made a correct decision. If this is true, we reject the null, we did right. If this is true, and we didn't reject it, we've made a type 2 error. Some bias is possible. Suppose a factory is being investigated for dropping pollutants into a nearby stream. There's a certain maximum level allowed by the government. Should sound familiar. Logical choice is the mean level is equal to the maximum allowable. 2 choices are possible. We could have the mean level as less than the maximum level. And you can see what happens if we reject the null versus not rejecting the null. But if an environmental group conducts the test, they might do it a little bit differently. This would be their null hypothesis, or their, alternate hypothesis, sorry. And they're suggesting, in other words, that we're polluting too much. Check that out. So it's quite different depending on which way you look at it to begin with. The right-tailed test creates one situation, left-tailed test creates another situation. And that's about it for hypothesis testing for population means. And I'll see you next time when we talk about population proportions. Very similar, just that we've got a few formulas that are a little bit different. Everything else, the logic is really the same. Until then, see you later.